By far, the most common way to look at EEG and MEG data is by looking at event-related potentials and fields, ERPs and ERFs. So we are often interested in what is specific to a certain manipulation of our experiment, like differences in stimulus parameters, let's say words versus pseudo-words, or pictures that refer to living and non-living things like that. So that means you want to get the data for your for one condition, for another condition, and contrast them against each other. And that is usually done by averaging. So you average your data for different categories of stimuli or different tasks, possibly for different participant groups, and then you compute the contrasts between or among them. So this is what we are going to deal with now. I am also going to mention parametric analyses at the end briefly. Averaging is not exactly an exciting topic. I think we all know what it is, but there are some implications for some choices that you've got to make, some implications maybe for the interpretation that I think we should go through here. So the idea is really very simple. You present your stimuli many times because a single presentation of a stimulus usually doesn't do much to brain activation, at least not compared to the ongoing resting state activation. So it is possible to see single trial responses, as we will see later, but this is not usually enough to draw any meaningful conclusions from it. So we present our stimuli many times. We mark the time point in our data, usually the onset of stimulus presentation with a trigger, a number. Then we can later cut data segments around these time markers, these triggers, out of our data and average them together. And that will be an event-related potential or field, in this case, a potential from EEG data. One trial won't really show much. That's just basically just one little piece of ongoing brain activity just cut out. If you average 10 trials together, then in this case, and I think that was a visually evoked response, you see something like an evoked response emerging here. It's slightly higher than here in the baseline period. Obviously, before stimulus presentation, we shouldn't really see much, at least nothing that's specific to the stimulus. And after 80 averages, we are in business. So we have a relatively small baseline and an evoked response in multiple channels here. So that's what we want. So ultimately, we want something like that. And this is just to show how you can visualize these data. So we will get an evoked response for every channel. You can plot the time courses of these evoked responses, for example, as overlays or butterfly plots for all the channels. In this case, the lines are color-coded. So the front left channels are green and the back right channels are reddish, for example. And this is a nice evoked response. So you have this positivity here in the back. So you could therefore call this a P1. Maybe this because it's negative in the back, and N1. I actually think this is an auditory evoked response, but never mind. So these are just labels. I mean, you may attach more significance to labels like that, P1, N1, N400, P300. But first of all, they simply describe a certain type of topography in a certain latency range. So they are labels. It's interesting also to visualize averages, basically where these averages come from, like this. So this is a plot that actually shows every epoch for one channel, in this case, an MEG channel. So every epoch is, or the time course of every epoch for this channel is plotted as one line of this matrix and then color-coded here. And there you see the individual responses sticking out. So you can clearly see that in almost every epoch, there is something like an evoked response at 100 milliseconds. And if you average that together, not surprisingly, you get this kind of curve, which shows you this positive value here around 100 milliseconds. But it does show you that there is something going on in at least most of your trials. I mean, in theory, if you order this with time, you may check if they diminish over time, for example. You could now order these epochs based on reaction time or stimulus parameters, word frequency, what have you, and see if that changes anything in amplitude or latency. But I think it's a very interesting way of displaying your data. Another common way to display data is channel by channel, and this topographic arrangement. You can easily get plots that are very hard to interpret, but it might help you to, to check the data quality, to see that everything's plausible. Maybe you'll see something that you hadn't noticed before. I mean, in this case, I think that's an auditory response. So you have your evoked responses here in the lateral channels, not that much in the posterior channels. So there's MEG in this case. But one thing I think that's important to realize is that the average might actually lose information, or at least it might reduce some amount of information. So this was this is a figure from a paper that was one of the first to look at the evoked responses or event-related responses in the time and frequency domain. But that's something we'll talk about later. But what we usually assume is that we have a brain response that occurs at a fixed time in every trial after stimulus onset, and it is always exactly the same shape. So let's assume we have this mini oscillation here, confined in time at a certain frequency, and it appears at exactly the same time and exactly the same shape, exactly the same phase. And in the average, we just get this signal back, which is as it should be. So now imagine you have this kind of signal more or less happening at the same time after stimulus onset, but it's just a bit jittered from trial to trial, sometimes a bit earlier, sometimes a bit later. So in this case, positive values and negative values may average out, and the average in the end might look relatively flat. So this already shows us one thing. So first of all, the average response is confounded or is modulated by two factors. First of all, the overall amplitude of your signal. So if you have two conditions, and in one case you have large responses, and in other words, small responses, fair enough, you will see this difference in the average. However, even if amplitudes are the same, if one condition has larger variability compared to the other, then you may have a smaller response in the condition with larger variability. And this might potentially produce an amplitude difference in the average. Also, people, at least a while back in the literature, they distinguish between evoked and induced responses, so that might be interesting in itself. Some responses might be more or less time-locked to stimulus onset and maybe confined to a particular frequency range, but they might still jitter a little bit with respect to the phase of this frequency band response. So if you have something like that, yeah, then you might miss something in particular frequency ranges, let's say oscillatory responses, simply due to averaging. And one way of addressing this is by not averaging these original EEG or MEG responses, but to look at them to compute power in the time frequency domain. And that's going to be something we will talk about in a separate section here. So I will stick to the more boring averaging in this session. I mean, if you're averaging your data to compute ERPs and ERFs, one question people always have is, how many trials do I need? So how many stimuli do I have to present to my participants? And the answer to that is it really depends. There simply is no clear answer to that, because it does depend on the size of the effect you're interested in. If you have a huge effect, then you might just need a few tens of trials. If you have a tiny, subtle effect, then you might need hundreds, or you might not. Yeah, maybe you will not get any effect at all. So it's really not clear. So a statistical power analysis is really a good idea if you have data to actually do that properly. Otherwise, well, I guess you'll have to learn the hard way. Just a few principles here. I mean, for random noise, variance goes down with n, and the standard deviation goes down with the square root of n. So that obviously means that the more stimuli you have, I mean, the less benefit you get from adding just a few more. If you only have 10 stimuli, you can add 10 more. Well, then you have improved data quality quite a lot. So you're basically half the variance. If you have 500 stimuli and you add 10 more, then that's not of very much value. So if you can increase your number of stimuli, especially for those conditions that don't have many trials, then that will get you the most benefit. If you have rare artifacts or even just a one-off artifact, then the amplitude goes down just with a number of trials. But if you have something like that, then you've usually done something wrong. So you should either mark these data segments as bad or apply artifact correction, something like that. I mean, with eye blinks, for example. There are robust averaging procedures that give different weight to different trials, depending on how noisy they are or how far away they are from the average. So if you're interested in that, you have to search for robust averaging. I think SPM has something like that. And what I already said, I'm just trying to highlight it here again. The average will always be affected both by the amplitude of the signals across trials, but also by the jitter or the variability of the activity across trials. Usually, we try to make sure that we're not doing something completely stupid by removing epochs that have excessively large amplitude differences. So we usually specify a maximum minimum criterion. We compute the difference between the maximum minimum amplitude within an epoch. And if it exceeds a certain value, and these values are usually chosen quite heuristically, then we reject these epochs. So that's to make sure we don't include anything that might be just due to a bad electrode that might produce a big jump in the signal due to a movement or something like that. We should always make sure that chronically bad channels are excluded from the data in general. But if you still have a bad channel and you apply this kind of minimum maximum criterion, then you might not have much data left in the end. So therefore, if you find out that your artifact or your averaging rejects lots of epochs, it's always a good idea to go back and see why. Is it because of a particular type of artifact or a bad channel? So then you could potentially still do something about that. And if you apply any procedure that combines signals across channels, I mean, like signal space projection or ICA, which usually applies some spatial filtering to your data. So you should definitely make sure that bad channels have been removed. Also average reference for EEG, such a procedure, because otherwise the noise from one channel might actually be transported into all the other channels. You should always make sure that your data artifacts have been removed before you average and apply any artifact rejection. So ICA, for example, should be applied beforehand. And you might think if you rejecting a whole epoch, maybe just because there is an artifact in a few channels, can be wasteful, especially if you have very precious data, let's say from only a few patients, or you only have a few minutes of recordings and so on and so forth. So rejecting the whole epoch is usually playing it safe. So if something is bad in a few channels, there might be something bad in the whole epoch. But if you don't agree with that, there are methods that try to rescue as much of your data as possible, like, for example, the auto-reject method in MNE-Python. But ultimately, the proof of the pudding is in the eating. So check the quality of the data that come out of your averaging procedure. You can compute signal-to-noise ratios. That's what you ultimately want to improve. Look at what's happening in your baseline periods. Are there still some channels that are much noisier than others, and so on and so forth? And then you can always go back to the beginning and say, okay, I will mark more channels as bad. I might filter differently. As long as you do that without looking at the actual p-values that you're interested in, that's allowed. I mentioned auto-reject. I'm just trying to highlight here. So in principle, you could have a very complex pattern here where maybe some channels are completely bad. Some epochs are bad, where all the channels are bad, but then in some epochs, you might just have some channels that are bad. So if you want to make sure that you only reject what really is objectively bad, there are certain methods based on cross-validation algorithms that can average in a more sophisticated way. So this is something you may want to look into. But now I want to briefly talk about alternatives to this kind of factorial averaging, where you average, condition A, condition B, and then you subtract. With behavioral data, I think everybody will be familiar with regression analysis, where you look at continuous variables, let's say the length of a word or the number of pixels in an image or some valence and arousal in some natural pictures. Of course, the same can be done with EEG and MEG data. So what I've described so far is the factorial approach. So let's imagine you have short words and long words. You usually try to optimize your design that you have very short words and very long words. And then you average for short and long separately, and then you subtract. And that means that you're potentially throwing away information about the continuity of this variable across trials. It also means that you might select very awkward stimuli, because maybe all the long words have certain properties and all the short words have certain properties that are possible confound that you're not interested in. So another approach is to use the whole continuous information in your variable of interest and regress that against the ERP or ERF amplitude for every single trial. So this has been, this is actually the general linear model that is routinely applied to fMRI data. So with fMRI data, you have to apply a model like that because you have overlapping brain responses. With EEG and MEG, this is not usually done because you don't have overlapping brain responses and you can get the individual averages and therefore clearly separated brain responses. But now if you want to do something like that, because you have continuous variables, so you don't want to average different conditions separately, then you can. It's linear regression, multiple linear regression applied to EEG and MEG data. The idea, what you're doing in the end is basically averaging just in a slightly more sophisticated way. So if you do regression or multiple regression, what you get is different weights for every single trial. So in normal averaging, you would weight every trial with 1 in one condition, with a 1 in every trial in another condition. Then you divide by the number of stimuli, of course, in the end. If you apply regression to your data, different trials basically get different weights. And you get a weighted average rather than a simple average at the end. So it's basically a more generalized way of looking at averaging. So but what we've talked about before about rejecting epochs, for example, artifact correction, I think all this still applies. And this is usually the only way to actually get meaningful results from more complicated, complex experimental designs. For example, if you use more naturalistic experimental paradigms, let's say you're not studying words in a word-by-word paradigm where you present a single word every 2 or 3 seconds and you let your participants press a button if it's a word or a non-word or something like that. So if you present them with continuous text, either speech or text that they can read, then you somehow have to deal with the overlapping brain responses and also with the fact that you don't have properly matched conditions anymore. So you have to include a number of covariates. And I'm not going to go into very much detail, but what you then basically can do is approach your data with a regression design. So you can use features for every stimulus type for every trial and analyze your data in a more continuous way. In the auditory domain, there's, for example, a toolbox by Cross et al. They apply this kind of large-scale regression model to natural, so to EEG, possibly MEG responses from natural speech. And they call this the temporal response function, what they basically get for different stimulus properties out of their data. Very similar approach has also been developed to analyze data from natural reading. That's a very similar problem. So if you read a sentence naturally, then you don't have your words, every few seconds. You have them every quarter of a second approximately. Average fixation durations are usually in the range of 250 milliseconds. So brain responses are overlapping, and also you don't have properly matched stimulus categories anymore. So you need to include a number of confounds, covariates, and on top of that, you have artifacts in your data, but that's something we dealt with in another session. And for that, you also have at least one toolbox now that basically works with a large-scale regression model that gets you these brain responses for different parametric modulators, let's say word length, word frequency, what have you. And then for these different betas in your model, you get something that looks very much like an evoked response. And in fact, it's comparable to a difference response in the factorial design. So let's say you have long and short words in the factorial design, you compute the subtraction. What you get there is comparable to what you would get for the regressor word length in a model like that. So you can interpret these results from these regression approaches a bit like evoked responses, but difference responses. Just 2 caveats. the polarity of these effects, I mean, the beta values that you get out of your regression model are harder to interpret because when you apply these models to sign data, like positive, that have positivities and negativities, then a positive beta value could either mean that you have a positive ERP, which gets more positive with your variable of interest. Let's say longer words might produce larger positivities, larger overall amplitudes. But it could also mean that, let's say, a negative peak becomes less negative. So overall amplitude goes down, goes closer to zero. So longer words might produce a smaller negative, a smaller N1 peak, for example. So there's some ambiguity in there. And unfortunately, this, that's ERPs and ERFs for you. And also some higher level or most higher level analysis methods, such as connectivity and decoding, as far as I'm aware, are still designed for factorial design. So they assume that you have two stimulus categories and you try, you compute connectivity for one and the other, and then you subtract them from each other, you compare them with each other, or you have two stimulus conditions and you try to decode them. So hopefully, methods to deal with this in a parametric fashion will emerge, or maybe they have already emerged somewhere and I just don't know about it. Okay, well, that's it for now.